It's a high-profile location. That's the San Diego airport in the distance. You can see the water. It's at the corner of Vine and Kettner. Kettner is one of the main thoroughfares of all the traffic in the morning going to the airport, trying to catch their flights. So track out all the sweepy, the BMPs was a huge concern early on, making sure that we didn't, on this high-profile job, we just want to make sure we kept it clean. So right here is the final configuration. So you can see that parking lot, and we converted basically into a fully functional 69 kV substation. You can see some of the major components included a new CMU wall. It's an 8-inch split-face block wall. See your switchgear on the left of the substation there, and your racks. And update, the steel is going to be starting here in a few weeks. The banks have been delivered and all the major pieces of equipment. Right now, the breakers are going in. All right, talk about site development real briefly. The contract was broken up into 6 different tasks. That's how we used it to track schedule and to track billing. Obviously, every project, you had your BMP setup, your office trailer, you had your security fence, traffic, and all of that. We had demo, so obviously it was a parking lot. We had to remove 62,000 square feet of paving, all the driveways. We had to remove a street light and do some salvaging of some signs. We went into some site prep and grading, so clearing up, removal. We had a couple of trees that we need to get rid of. In fact, if I allow me, I'll back up a few clicks. Those palm trees you see here, because there are so many, there's components of this project, a lot of coordination, and one of those aspects had to do with the monitors we had on site. So even to remove those palm trees, we had to have monitors basically spend the night, camp out in the parking lot, and monitor those trees to see if they were looking for the Mexican long-tongued bat that was suspected to be inhabiting those palm trees. And when they found out there were no nests, at that point we were clear to remove them. But obviously documentation, making sure that all of our ducks in a row before we proceed with work. So we obviously had a bit of export material. We'll talk a little bit more about that in a few. And then eventually a lot of Class 2 base and select fill import. There's a bit of drainage related to the work during site development. We had some storm drain pipe to put in, different cleanouts, ribbon cutters, what have you, part of the site drainage system. And last slide here. We did the street improvements. This is the chunk of work that's still pending. So we'll be starting this work in October. This work is just waiting on distribution to make their final connections to our substation, and then we're free to do the final improvements. And then we did mention we had the CMU block wall, we have a new control building, and new gates, that sort of thing. Some photographs of the process as it shook out. So the very first picture, top left, you can see the removal of the AC paving. That was week 1, fairly straightforward work, not much to it. Then about a week later, when we were in our Mass X, we found what you see in picture 2, which is basically the world's longest unknown footing. And if you guys recall, this used to be a gas station back in the 70s before it became a parking lot. And that contract at the time, they found it more cost-effective to just bury this, and it was about 3-4 feet underneath the asphalt. And so right away, we had an impact to our schedule. This is our critical path. And if you guys know me, you guys know I love my schedules. And right away, we're looking at the schedule, saying how is it going to impact, what's it going to cost, so on and so forth. And we had the contractor wasn't quite prepared to deal with this type of work. And at the time, it was like a 303 Mini, but it was a pretty small excavator we had out here with a chipping gun. You're breaking away this concrete, and while another crew was exposing more of it, we were realizing, we need to bring out the big guns here. So feeling like they were digging their way to China with a teaspoon, we asked, we coordinated with the owner, make sure they were comfortable with the upsized equipment, and we were able to get a bigger piece of equipment right away to start mitigating some of this delay to chip out this unknown thing faster. And so the it's going to be a relative common thread through this talk, which is you basically want to keep open lines of communication at all times just to get the best mousetrap built. In this case, it was mitigating this footing. 3, we had the scraper operation going through and removing, the first 5 feet was what was in the bid item in Patriot bid. And with the geotechnical engineers on site, they realized that further. So the first 5 feet thought was going to be enough to get you into native material. Unfortunately, they realized that it would take another 5 feet of digging with scrapers to get to native soil. And so obviously more scope, money, more changes, and once again, we're right back to schedule and talking TIAs to try to forecast how it's going to shake out. Do we need more equipment on site? Do we need more crews? How are things going to shake out? And obviously, this impacted. This talk is relatively short. I could talk forever about this project, but you open up a whole new can of worms. We're now shoring, it's the street side now that we're going so much deeper. And we had a lot of meetings to try to get everyone involved, just to, have Vegas rules discussion of just, if it's a concern, let's speak up now and let's talk about it, see how we can address it. Picture 4 on the lower left is the footing. So once we got past the Mass X, we were off to the races building our footing for the CMU block. And it's fairly smooth sailing until we got the world's worst rainstorm event that ended the California's drought and 92,000 gallons of water to fill the substation. Once again, this was, our owner, SDG&E, was looking to find out how we can mitigate and schedule impacts. Once again, it's a critical path impact. We have standing water. So hosting a meeting with us, the engineers, the geotechnical engineers, we brainstormed all sorts of ideas. We can maybe using lime to accelerate the process, too much environmental red tape. We ended up going with scarifying, ripping the soil. So for a minute, it looked like a farm inside of our substation with the rows of piled dirt. And but we were able to accelerate the drawing process a little bit faster. We did get approval on the additional cost to do this, to increase surface area to maximize drying. But in the end, I think the owner was happy with our decision to help mitigate time impacts. And finally, our last picture there is basically the final setup of the development setup. You seam your wall all the way around, and you're looking at about 6 inches of Class 2 base, gives you a nice clean layer to work, and allow the below-grade contractor to start ripping everything up again to start installing their foundations and their duct banks. All right, so, excuse me, so below-grade finished. All right, Development finished their work around January, February. So February is when we were clear to start the below-grade portion of work. So quick scope cover. We had, you can see there's 3 oil containment pits, pads for the banks. So you guys can see my cursor here. That inside area is the actual foundation. It sits a couple of beams for the transformer bank. Outside is the oil containment structure for each bank. Firewall foundations with drilled piers for each firewall. So here, there's another one that sits right there. They're just blast walls in case one, with a domino effect of one transformer bank failing and setting off a reaction with the rest of them. Mainline system. So the below-grade contractor was tasked with putting this in. So we'll talk about this for a minute. It's a unique, actually really cool. So the way it works is the oil containment, secondary containment system for the banks is basically just an open pit. Catch any oil in case the transformer ever leaks. And these things hold thousands of gallons of oil. So they have basically a chemical valve at these, 3 ports here that allow rainwater to flow through, and it seals up the minute you get oil. So it doesn't allow oil to go in. The reason we want oil is because the system, see it flows here, goes down, this pipe, and then it connects into one of these 3 inlets, basically connect to the other side of the CMU wall and route into the city's storm drain system. So it's a massively huge deal to make sure you don't ever allow oil to just flow right into the city's oil storm drain system. So it's one of those where you want to double check your specs, make sure that everything's installed correctly, and once again, get that coordination going. Switchgear pads, we had 3 switchgear pads that we put in, pretty straightforward. Drilled rack pier foundation, we'll talk about for a minute. There were several piers of different sizes that support the rack, the steel rack, that's the switchgear. Track, sorry. So these piers, the contractor, in their ideal world, they would, come in, they would drill all the holes for the piers, and eventually drop in some rebar cages, fill them with concrete, and life is good. But if you take a careful look at the spec, the spec is very specific about how long you can leave these excavations open. And the concerns, talking to the technical engineers, has to do with relaxation of the walls of the excavation. So that's why they're very restricted on the amount of time this excavation is left open. So that being said, we required, because we had a pre-con meeting with the contractor, and he almost casually said, sure, we'll basically put the concrete according to what the spec says, but we required them to put together basically a mini 3-week. It's how they were going to sequence the work and where they were going to be to schedule inspection, and just to make sure we're all on the same page in terms of not bite off more than they could chew or close at, within the audit. So a couple of circuit breaker pads. We had, if you guys look on this drawing, this is the 645 drawing, so it shows all the duct bank layouts. The dashed lines are all the power conduit. The solid lines are the control. And this will be important a little bit later here, but there's a lot that I learned being on this project. Obviously, we had the new control shelter. Look at some photographs here. Top left photograph is the foundation for the control shelter. You can see how many penetrations, how many steps you have, different sizes, just for one building alone. So, all control comes here. The CMU block was super fast. I mean, it was Vic Roth Masonry was the subcontractor doing block work, and they built this shelter in about 2 days. You have New Electric putting in some of the conduit runs for the control shelter, and if you guys look closely, you'll notice that right behind this guy here, see some of the duct bank or some of the conduit runs. They dive right into what looks like a backfilled area. And I'll use this photograph to highlight how often the design was changing on the below grade portion. It changed so often. The on-running joke here was just build it as fast as possible, because if you don't, it's going to change 5 more times before you put a shovel on the ground. So it's constantly changing with groups within the agency wanting different size conduit, number of conduit, spares, that sort of thing. So it was a real challenge tracking all the changes and bundling them up during this phase of work. But that's an example of how we were dealing with the changes as they came up. Left here, you can see basically a fully built transformer foundation pad and the secondary containment structure. And you see the guy here on the western. So the backfill couldn't really happen until obviously your grounding grid is installed. And we'll talk more about the grounding grid in a few. But one of the quality control items that came up, lesson came from this, was that there's a key. So let's back up a little bit. The grid, there's a couple of ways to connect a grounding grid. You can do an exothermic, connection, or you do a mechanical crimp. And on the job, they opted for mechanical crimp. But the question is, how do you know if the connection is good or not? And so what I received basically was a key, where the key fit over the crimp that was made at, say, an intersection of 2 grounding wires. If it, that connection was good enough. So it was a matter of keeping track of a crimp that was made, but also making sure you'd had an opportunity to test it before the backfill was done. So that was a pretty massive undertaking, working with the FCAs here at SDG&E and making sure we had a good understanding of what had already been checked before it went in. Here you can see some of the the bank runs, and these things are massive. So you can see the shoring that's in place there. Some of these are 5-inch conduit. They're 8 by 8. Depend on the run, but they're pretty big, and they really limit your access. So every week we would basically discuss where certain sites, areas of the site would be basically closed off at any given point before they were backfilled. Here, you can see we're standing in front of the switchgear foundations. You see stub ups come up. And I threw this photograph in for a second reason, which is to highlight Glow. So Eric, I think actually Glow last time you were here, but she's been with SDG&E for over 40 years, and she has so clout with the agency, and she's very much become a mentor to, and enough so that, a lot of these projects where there's, if ever any apprehension about outside consultants coming in, she's 100%, out there rooting for us. So she knows the value that we bring, and it's about developing and maintaining the relationship that we have with people like Glow. So I definitely strongly recommend, we reach out and we establish these relationships with the clients that we have, because it's invaluable. I mean, she's taught me so much. This is a project I work with her on. She's been just a huge asset for me. So get into some lessons learned. What do we got? Okay, so drain. Okay, so if you can imagine, you have a rectangular. So site development is done. So they leave behind basically a CMU wall perimeter, and you have a bunch of select fill dirt, and then you have about 6 inches of Class 2 base. In the dirt, and in between the CMU wall, so in between those two, sits this drain board. And half of it looks like felt. The other half, you can imagine, looks like plastic Legos. And what works is you take this sheet and you put it vertically in between the dirt with the plastic side on the CMU wall side. So that the dirt sits up against the felt, and whenever there's groundwater from a storm, it penetrates down through the Class 2 base, works its way into the dirt, and water now has a place to go. It doesn't create or place a surcharge on the CMU block wall. So the water migrates through the felt against the plastic Lego looking thing and fall down through Legos, and then eventually pop out through something like the universal T. And it seems like a relatively simple concept, but even Tyson saw this one. The entire substation was designed to drain towards one corner. In this case, it was the northwest corner of the substation. And based on the way it's described it, is if you can see this universal T, these are designed to have the T part, or that cup, come on the felt side. But in this application, we reversed it. We made it so that it would drain to the corner of the substation and pop out through the seam wall. We had already backfilled, the drain board was in, we're backfilling, and at some point I was taking a stroll around the corner of on the outside wall, and I put my head in and I realized plastic is still intact. Wondering how the system was going to work, how it was designed, I etched up this picture you see on the right, kind of explaining what I was seeing, and we got the conversation going. And it turned out 100% needed to pop that hole. If it didn't pop that hole, all the water draining inside the substation would work its way along the wall, along the inside, ever come out. So that could have been a huge deal, and just want to reiterate, that's why we're here, to ask all the dumb questions. And if you're not sure, just ask. I mean, in this case, it seems straightforward, but unless one of us, it was never going to happen. For you, lesson learned. So it is the outside of my substation, and I'm looking at the CMU wall. And that dugout trench there eventually became the bioswale. So contractors would come in, they'd put a layer at the bottom, and they'd put in different layers of media, different layers of rock, number 50 sandstone, so on and so forth, to build what looks like almost like an aquarium filter. And it percolates at a certain rate, so on and so forth. But the point story is this, is Vic Ross, the C-Block subcontractor, was off to the races building their CMU wall, and they built it in lifts. I think it was 5 lifts in this case. So they up a couple of courses of the block, they grabbed, wait for keep building up. At some point, we ended up with basically a very long, very tall freestanding wall. The question came up was this wall designed for? how much wind loading, and we just started asking the questions. And so with type, we were able to get a copy of the design calculations from the design firm Brady that designed this wall, and called in the subcontractor. How do you guys support the wall in the interim period before its final configuration? He's been doing this for how long? 40, 50 years. And he laughed. He said, you're literally the first person to ever ask us this, and we never look at calcs. And Bryce and I were looking through the calcs. We realized that part of the wind loading capability of the wall was based on having about 10 feet of backfill on one side of the wall. When this case, we didn't have it. It was still being built. We had a group that it might be a good idea to put some pole braces up. That decision was further compounded by the fact that here in San Diego, right in downtown, miles from us, there was a wall that came down during construction and actually killed a worker right at the time that we were having this discussion. So it was on everyone's mind. So she did make the call, and it was relatively inexpensive. It was a few $1,000s to put in these pole braces. But I mean, it's a small price to pay for the relative safety you get from it. Yes, it would take quite a bit of wind, but why? Why risk it? And so that was a question that we raised, and we felt made the right call on that. I'll the last one, then I'm done. Okay, so the grounding grid. So for those of you guys not familiar, there's a grid inside of every substation, and it's designed to reduce your step potential. So to make sure you're basically always at the same potential as all the stuff around you. Because the minute you have a difference of potential, that by definition is what causes current to flow, so forth. So the question is, at what point do you get your grounding grid design? So the picture on the left is the grounding grid that the contractor was given. It's for a substation called Sorrento, and it's pretty different from our station, which is the one on the right. And so I thought it was odd at the time, but they explained to me that because the grounding grid design, the density of the grid, is actually a function of the characteristics of the soil. In other words, it's not until you actually import all your soil for the first time able to actually do a grounding grid study, that they're able to check the conductivity. So they put one probe in, another probe in, and they can tell how conductive is the stuff in the ground. And based on that, they go back and they design this grid. So you already have a kind of an upper limit or a lower limit about how quickly you can get your design out. So the below grade contractor is chomping at the bit, trying to get, he keeps asking for this design. And I asked, well, what did they bid off of? And they bid off of the Mira Sorrento grounding grid plan. So what I did was I took that plan and I put a blue beam and I did a quick takeoff. And we figured out how much exothermic connections, how many ground rods, how much 4-aught wiring you have, how much 500 kc mil do you have, and I came up with these totals. And then I was going to compare it with the new design that we had just received. But, what was interesting was that a couple of things. That one, unfortunately, the agency, SDG&E, had provided a contractor at bid time, obviously the Mira Sorrento grounding grid, but also quantities of numbers. And so it's a problematic system because it turns there was about $8,000 worth of delta between what handed them, between the drawing they handed them and the quantities they gave them. So in other words, their takeoff was wrong. And the contractor ended up, the argument was, well, we were given these quantities, so on and so forth. So a couple lessons learned, and communicating this with the managers at SDG&E, I think that $8,000 difference from a quick takeoff using Bluebeam, we have ways. One is, where possible, if we can streamline or find a way to prevent things like this from happening, we want to try to communicate this on that it may not be the best practice to do this. Two, I think everyone should have Bluebeam. It's a great tool, and it took me 20 minutes to sit down and do a quick takeoff. So if you guys don't have it, please get it. I do have one other, bear with me, talking fair. I want to cover this slide here. If you guys can see it, and can I zoom in? I cannot. Okay. a look where I'm circling here. It just came up. And in fact, we're doing this right now. With these capacitor banks, capacitor bank D and C, the only thing I want you guys to look at is the dotted line versus the solid line. In drawing, the dashed lines are the power conduit, the solid or the 3-inch communication lines. Last week, Kearney crews, who are the in-house SDG&E teams that build all the above, they plop down the equipment. So they plop down the capacitor bank, and they realized the communication and the power are flipped. They can't win. There's no way to Mickey Mouse it to make it work. The only way is to rip out the conduit and we do it. So I thought, oh my gosh, what's going on here? I went back to the drawings, and it turns out they were built for the way the design was. But doing more investigation, found out that one electrician apparently had actually brought up from a job that he thought this was odd, that they had flipped these two on design. Unfortunately, instead of bringing it up, which it's free to ask, as my dad would always say, if you think something's wrong, we want to encourage an environment where everyone is just free to bring things up, because this is going to be a fairly expensive out at the end of the block. You have to recompact, run new conduit, report. And so we could save all this by just stressing to everyone involved. In fact, I need to do a better job at this too, which is if you see something, bring it up. We didn't have the manufacturer, the companies basically for the capacitor banks. So this could have been an easy check had we just run it up the flagpole, but we didn't. So it was built per plan, but it's an easy fix before you actually pour everything. So that being said, I think I am done. A couple of things I wanted to talk about. Lastly, as Eric, I think you shot over an email to everyone with my original presentation when I started this project, and putting this final report together. There's a hard copy of my report. It's a couple pages long, but putting this final report together was directly connected to all the upfront research that we did. And at the time, we were only expecting to do the site development, not below grade. But the secret is, one, start early for sure with all this work. And as you do it, just update the report. It's the easiest thing. As things come up, you just plop them right in. In fact, Tyson would come visit the site, and he'd say, sounds like that's a great lesson learned. And guess what? That same day, we'd just do a quick write-up and just throw it in, because doing it after the fact is really, really challenging, trying to jog your memory. Guys, that's all I have. If you guys have any questions, feel free to shout them out.
Carlos.
Oh, thank you.
Yeah, good job, Carlos. Good job. Nice done.
Awesome. Thank you. If there are no questions, I guess everyone thanks for taking the time to listen. And if you guys think of any questions, feel free to email me. It's a pretty awesome project to be on, and wish everyone a happy and safe 4th.
Thank you, Carlos. Fantastic.
Thank you.
One quick thing. In the beginning of your presentation, you talked about how we were lucky to get on to the below grade and the above grade. I want to clarify, it's not that we were lucky, it's that you were doing a great job out there, and the client recognized the great job that you were doing and saw the value of adding that. So that was directly related to the work that you were doing out there. So.
Tyson. Thank you very much, guys. And for the record, Tyson's been a huge help on this one. He's a great resource to have. So thank you, Tyson. Thanks everyone. So.
Great job, Carlos. Keep up the work, sir.
Thank you. It's okay. We'll talk soon.
Thank you.
Thank you.
Bye-bye.
Substation was built from a parking place and changed to